everyone. I thought I would step in here and give you a little bit more information about parametric surfaces that will be helpful to us as we kind of finish out this vector calculus that we've been learning. Remember that not every surface is a function, right? And so for surfaces that are not functions, the question is, how could we describe them, right? So things, for example, that wouldn't be functions would be things like a sphere or a cone, potentially, depending on how it's oriented. And there's a lot of other examples. Anything that does not pass the vertical line test, right? If you draw a line that's parallel to the z-axis, if it impacts or crosses the surface in more than one place, you don't have a function. Okay? So we're going to talk about surfaces and how to parametrize them. And there are several types of surfaces. I've got them kind of already outlined on the board here that I want you to be able to parametrize. Of course, if you do have a function, in other words, you have an equation z equals f of x and y, then you can parametrize it as well. In kind of a trivial fashion, it basically amounts to relabeling the two variables x and y as u and v. So if you have a function z equals f of x and y, you can just say, well, I'm going to let x equals u, I'm going to let y equals v. U and v are the parameters, and the equation then for z is just simply f of u comma v. So you just take all the x's and y's and change them to u's and v's. It's not really necessary to do that, but I like to do that just to kind of remind myself what I'm doing. I'm parametrizing my surface. Okay? Now, there are other types of surfaces that we would also like to parametrize. A sphere. So let's imagine we have a sphere. I'm going to assume that it's centered at the origin and has a radius of little a. So the equation of that sphere would look like this: x squared plus y squared plus z squared equals a squared. And we can parametrize a sphere. Think about the surface of the Earth, right? Imagine the Earth is a perfect sphere. Any point on the surface of that sphere can be described with just two pieces of information. When we're talking about the surface of the Earth, that information is usually the longitude and latitude coordinates of a point on the surface of the globe, right? So the longitude and latitude basically correspond to the angles theta and phi that we're familiar with from the spherical coordinate system that we've talked about in the past. So here you go. We can write down the equations for spherical coordinates. Notice that what I used to call rho, which is the distance from 0, 0, 0 out to a point on the sphere, I'm replacing that here with this constant number a. So a is not a parameter, right? A is just going to be a value that comes from the equation of the sphere. It is simply the radius of the sphere, which is just a constant number. The parameters in this description of a sphere are phi and theta. Okay? So phi is really representing the latitude, kind of tells you how far down from the North Pole you are on the surface of the sphere. And theta is measuring longitudinally where you are with respect to, the international date line going around 360 degrees in that sense. So those are the two parameters in this parameterization of a sphere. Now, if you only had, say, the top half of a sphere, which is just a hemisphere, then you could treat that as a function. You could solve this equation for z, and you would get, of course, the square root of a squared minus x squared minus y squared, and you could think of that as a function again. And so a hemisphere would be parametrizable as a function in that context, right? But if I'm going to take the whole entire sphere, then I need to do something else. And this is the best way to parameterize a sphere. Just use the spherical coordinates where you've replaced the rho with the radius of that sphere. Okay? What about a cylinder? Well, let's imagine that we have a cylinder that's centered along the z-axis here. The equation of that would just be x squared plus y squared equals the radius squared. And this is talking about the side of the cylinder. I'm going to draw a very small example of that here. So the side of this cylinder right here, okay, the curvy side of it, not the top and the bottom, but just the side of it, has the property that x squared plus y squared is equal to r squared if you have a cylinder of radius r that you have centered along the z-axis. How do you parametrize it? Well, here's a great way to do that. To describe the points on the side of the cylinder, I just need to tell you what theta is and what the z value is above the xy plane. So v, again, I'm kind of doing the same thing I did over here. I'm using an arbitrary parameter v for z. It wouldn't really be necessary to do that. You could just let z equal z, okay? But I'm just trying to remind myself that I'm doing a parameterization right now. So I'm going to use a v for that. And then theta is my other parameter. R is not a parameter, right? R is a number. R is a fixed, specific number that is given by the radius of that cylinder. Okay? Now the other thing I want you to realize, guys, is that if your cylinder is not oriented along the z-axis, let's say that the cylinder is oriented along the x-axis or the y-axis, you can still parametrize it. You can still parametrize it, but what you'll have to do is exchange the roles of these variables a little bit. For example, if the cylinder is oriented along the y-axis instead of the z-axis, then the y variable has to take the role of the v, which was what z was before. And then you would simply build your sort of r and theta equations around the other two variables again. Okay, so you could do a altered parameterization if your cylinder was oriented along a different axis. Okay, something like that. The other thing that we've talked about doing is a disk. And let's again assume that the disk is oriented along the z-axis here. And in this context, there might be some radius to the disk, but I'm trying to identify points within the disk, right? So notice I've written the equation as an inequality. X squared plus y squared is less than or equal to r squared. In this case, my r value and my theta value are variables. They are not constants, because in the cylinder, I was always staying out on the edge of this curvy side of the cylinder, so the radius was always capital R. But here, the distance from the z-axis is going to depend on where I am in that disk, right? There's lots of different points. Okay, so what this means is that I'm going to use the radius as one of my parameters, and I'm again going to use theta as my other parameter. This time, the z value, how high is that disk above or below the xy plane? That's just a constant. You can see here from the picture that the z coordinate of every single point that's in that disk is always the same. So I don't need a parameter to describe z. I just need to write down a number for z. Okay, so my parameters here are going to be r and theta. Again, I could choose to reorient this disk along a different axis. And if I did that, the roles of these three equations would have to be modified. They would have to trade roles a little bit to describe a disk that's, say, going along the x-axis or the y-axis. Okay? But that's something that we can also do. If you have a cylinder that is closed, in other words, if you're including the top and the bottom as well as the side of the cylinder, that's actually three surfaces, isn't it? It's three surfaces. It's the disk on top, the disk on the bottom, both of which are handled over here, and then the curvy side of the cylinder, which is what this column right here is addressing. Okay? So we've got functions, we've got spheres, we've got cylinders, and we've got disks. And I want everybody to be able to parameterize all of those types of surfaces. Now, once we've got a parameterization of a surface, maybe we're interested in writing down a tangent plane to that surface, or maybe we want to know the surface area of that surface. We've done this stuff already in the case of a function. Okay, so you might remember from back when we were learning about partial derivatives that the tangent plane to a function is just simply the following equation. Z equals Z naught plus f sub x of x naught y naught times x minus x naught plus f sub y of x naught y naught times y minus y naught. We talked about this back when we were learning about applications of partial derivatives, right? So here you see the partial derivatives, f sub x and f sub y, are showing up in that equation. This is the tangent plane to a function. And similarly, the surface area, we have a formula for that already as well in this first category, which is simply, we did a double integral over some region, which is the domain of the function with whatever part of that domain we want to find the surface area above. And then what we did is we took the square root of f sub x squared plus f sub y squared plus 1, and then dA. So I'm hoping that these formulas look familiar. These were applications of partial derivatives as well as double integrals that we've learned earlier. So if your equation is a function, you don't really need to parameterize it anyway. You can just write down the tangent plane or the surface area using what we've learned earlier. But then the question comes up, what if your surface is described parametrically? Okay, so I'm going to go ahead and erase here a little bit. Remember that, of course, you can pause and rewind and go back to look at some older things if you need to, and slow me down, send me some questions, whatever it may be. But let's take a minute to talk about how to write down the equation of a tangent plane to any surface, whether it's a function or not. Okay? So you have some surface here. And I could just imagine for a minute that what I have for the surface is not a function equation, but just a parameterization. Okay? And maybe there's some point on this surface where we would like to find, let me label this point, where we would like to find the tangent plane. Well, as you know, to write down the equation of any plane, there's two main things we have to have. One of them is a point on the plane, which would, of course, be this point right here, x naught, y naught, z naught. Okay? And the other thing that you need is a normal vector to the plane. I'll call that n. And we've talked about this a lot when we've been trying to understand planes in this class. And one of the things that we've learned is that one way to get a normal vector is to take a cross product of two vectors that are actually in the plane. Or in other words, that are tangent to the surface S at the given point. So it turns out that we can kind of verify this, that it turns out that if you take, okay, so if we take the parameterization of the surface, remember that what we're really doing is we're going to introduce two parameters. They might be u and v, they might be phi and theta, they might be theta and v, they might be r and theta, right? Any of those examples that we looked at earlier. But remember that you have basically a position vector that is telling you what x, y, and z are as functions of those parameters u and v. Okay? One of the things that we've learned is that when you calculate the derivative of the position vector, and in this case there's two different partial derivatives that we can calculate, what we get when we calculate the partial derivatives of these vectors, which is easy to do by the way, right? You just simply differentiate each component with respect to either u or v. Both of these vectors are tangent to S. Right? They are tangent to that. They're kind of like velocity vectors, right? A velocity vector is always tangent to the direction of motion. And in this case, it would be tangent to the surface S that it is sitting on. And so if these two vectors are tangent to S, then it turns out that if we just simply cross them, if we take the cross product, what we will get is a normal vector to S. Okay, so we're just simply going to, this is the magic thing this is the big takeaway from this little part of the lecture here, is that a normal vector to your parametric surface S is simply the cross product of the partials of the position vector. Okay, so that's pretty simple. That's actually pretty simple, and it's not that hard to remember that. In fact, you could even cross those vectors in the opposite order and you'd still have a normal vector. Remember that if you cross two vectors in the opposite order, it just changes the direction by 180 degrees. And if you do that, of course, you're just going to get another vector that's still perpendicular to the surface. So it's a pretty simple idea. So let's do a quick example here. Let's find the tangent plane to the surface. What I'm going to do here is I'm going to parameterize the surface. So let me give it to you explicitly here. X is equal to u plus v, y is equal to 3u squared, and z is equal to u minus v. Okay? Imagine that. And then we have to have a point. So at the point 2, 3, 0. Okay? So again, in order to write down the equation of any plane, I just need a point, which I was already given, and I need a normal vector. And my normal vector, as I've explained here, is simply the cross product of the partial derivative vectors of r with respect to u and v. So I'm simply going to, what I can basically do for the solution here, I can write down what r is. Remember, r is just the position vector. It's just x, y, and z. Just write it down, yeah? And then I can just differentiate with respect to u. So slot by slot differentiation is all you have to do. So when I differentiate each of these three components with respect to u, the results are right there. And when I do the same thing with v, I'm going to get 1 and 0 and negative 1. Okay? So there's your r sub u and your r sub v. The next step to get our normal vector, as you can see here, is just to cross those vectors together. So as usual, we're just going to build ijk. Okay? I'll put r sub u in the middle row, 1, 6u, and 1, and r sub v in the bottom row. And I calculate my cross product. I'm going to get negative 6u, I'm going to get 2, and I'm going to get negative 6u. Okay? This vector needs to be specific, though. I shouldn't have u and v in this expression. I need to have a specific, normally your vector is, 3 numbers, a, b, c. In order to figure out what the a, b, and c are here, I need to evaluate this at the appropriate values of u and v, which are the parameters in this description of the surface. So I need to know the parameter values. And that was actually not given to me. Right? So it's not given to me. I do know that x is equal to 2. I know that y is equal to 3. And I know that z is equal to 0. What you have to do is take these equations and figure out what u and v are. It's not really too hard. The last equation forces u to be equal to v. And if u and v are equal, but they add up to 2, then they're both equal to 1. So the values of the parameters at the point that we're looking at are 1 and 1. By the way, this set of equations always has to be solvable, because otherwise the point that you were given was a bad point that wasn't on the surface. Okay? So if you actually have a legitimate point on your surface here, then you'll have a set of equations involving u and v that you can successfully solve. That actually has to happen. Okay. If I now plug in u equal to 1 and v equal to 1, I'm going to get a very specific normal vector right here. Okay? And so with that, I can then write the equation of the plane, right? We have negative 6 times x minus 2 plus 2 times y minus 3 minus 6 times z minus 0 And all of that has to add up to 0. So there's the equation of the tangent plane. Okay? So just in summary, the tangent plane to a parametrically given surface, such as this one here, right? All you have to do is take a point and a normal vector, as usual, as we learned way back in the beginning of multivariable calculus. And to get the normal vector, we simply cross these partial derivative vectors of the position vector r. Okay, great. So that handles that part. What about surface area for a parametric surface? Well, it turns out that to do the surface area, there's going to be a very simple formula for that as well. Essentially, if you look at your surface again, just imagine you have your parametric surface here, right? The parameterization that you're doing on the surface is actually, it's chopping up your surface into these little parallelograms. These are approximately parallelograms when you've chopped the surface finely enough, right? It's like a parallelogram. And we've already seen an application of the material in this course to finding areas of parallelograms. And it's simply that the area, the area of the parallelogram formed by two vectors along the sides of it, such as what I've drawn here, is simply the magnitude of the cross product of those vectors. And these vectors are actually precisely those tangent vectors r sub u and r sub v again. Isn't that great? So the partial derivative vectors r sub u and r sub v play a huge role in what I'm talking about here, right? They give us a way of calculating a normal vector to the surface, and they also give us a way of finding the area of one of my little parallelograms. And then, of course, I'm going to do a double integral over the whole region that I'm looking at the area of. That double integral will give me the full surface area. So what's the formula for the surface area? Well, it's pretty simple. It's simply a double integral over the region. Now this region will be some UV domain, or that could be phi theta, or it could be r and theta, whatever the parameters are. This is the parameter domain that you're integrating over right here. And then all you're going to do is take the magnitude of the cross product. This is the area of a parallelogram that has side lengths r sub u and r sub v. Side vectors, r sub u and r sub v. And then we have dA here. And as usual, you can choose what order of integration to integrate your two parameters in. But that's the formula, okay? So a very, very simple thing to remember, I think, I hope. And it works really nicely. Let's go back to that example that we just did. And let's just do a little follow-up with that. So example. So remember, we had x equals u plus v, y equals 3u squared, and z equals u minus v. Okay, so this is a parametrically described surface. And let's find the surface area above the triangle in the UV plane. So I'm looking at the parameter domain, the UV variables, not the XY variables, but the UV variables. And we're going to take a triangle with vertices 0, 0, 1, 0, and 1, 1. Okay? So I'm going to draw a picture of that in the UV plane really quickly. I've got 0, 0, I've got 1, 0, and I've got 1, 1. So we're looking at this. This is my region R, as I usually refer to it right there. Okay? And so what I need to do is take the, let's just remember here, sorry. This was what we calculated just a few minutes ago. R sub u cross R sub v was, what was it, negative 6u, comma 2, comma negative 6u. Right? I think that's what we had. Yeah. Okay. So if we take the magnitude of that right now, we're going to need the magnitude of that when we use this formula. Well, it's going to be the square root of the sums of the squares of the slots, right? So 36u squared plus 4 plus 36u squared, or in other words, it's the square root of 4 plus 72u squared. Okay, so we can come over here then and use this formula to figure out the surface area of this parametrically described surface above this rectangle in the parameter domain. All right, I'm going to integrate u on the outside from 0 to 1, and then I'm going to integrate v on the inside. The integration limits for v would be from 0 up to u. Make sure you understand that. This equation right here is just simply v equals u. It's just a line, basically y equals x, okay? And then we put in our magnitude of the cross product right here, and then it will be dv, and then du. So this is the double integral that we have to calculate. I think I can safely get rid of the question here. You can always scroll back on the video and watch it again if you need to. But we're basically down to just solving this integral. And the outside integral, I'll save that for a moment. For the inside integral, there is no v in the integrand here. So when I integrate dv, and I evaluate it from u down to 0, I just pick up a factor of u. And so what I'm going to have is something like that. Okay? So I just get a u. And actually, we can now do a u substitution. I really hate to use that letter because I've already got u here as one of my parameters. But if I essentially take the part under, maybe we'll just use a w. If I take the part under the radical and refer to that as w, then the derivative of that, which is dw, would just be 144u times du. So I need to put a factor of 144 in there to fill out my dw that I'm going to substitute, but I have to pay the price for that by putting a 1 over 144 out in front. And after I do that, I've really just got the integral of the square root of w dw, and that's going to give me 1 over 144 times 2/3 of w to the 3/2. And then I'm going to go back. When you simplify 2/3 of 1 over 144, you'll get 1 over 216. And then I'm going to go back and put in what w was, 4 plus 72u squared to the 3/2. And now that has to be evaluated from 0 to 1. Okay, so we get 1 over 216 times 76 to the 3/2. That's when you put in u equals 1, we get 4 plus 72. And then minus, when I put in u equals 0, I get 4 to the 3/2. And this would be a perfectly reasonable answer. Okay, so there's the surface area for that particular example. By the way, I wonder what happens if we actually have a surface that doesn't really need to be parametrized. Right? So imagine that you just do the trivial parameterization that we wrote down at the beginning. Let x equal u, let y equal v, and let z equal f of uv. What is your position vector then? Well, here it is. The r vector would just be u, v, and f of u and v. If you take the partial derivatives, with respect to u, you'll simply get 1 and 0 and f sub u. And when you do it with respect to v, you'll get 0 and 1 and f sub v, whatever that is. Give myself a little more room here. Let's take the cross product and then take the magnitude, and let's see what we get. If you cross these together, right? So let me just do this kind of quickly here. You guys can check this in a little more detail, but the I component of that cross product is this times this minus this times this, negative f sub u. The j component is negative f sub v, and the k component is actually just 1. And if you take the magnitude of that, so this is for any function that is actually,